Hello, geometry friends. We have a problem here of the day, posted 8.5. Okay, this one requires quite a bit of setup. So in tensor calculus, we studied vectors and covectors. We wrote them like this. So we have a vector with contravariant components and covariant basis vectors. We call these tildes for the covectors, and they had covariant components and contravariant basis vectors, such that V acting on the vector acting on the covector, or vice versa, the covector acting on the vector, either one. We pull the components out front. We have this dot, the product, and by definition, it is the Kronecker delta ij, which is equal to 1 if I equal j, and otherwise it's equal to 0 if they're not equal. And this is a scalar, okay? In differential geometry, the basis vector, it's written like this as an operator. So it's written as an operator. And you see it has, with respect to this, the coordinate, but it's covariant. So this is covariant, this is contravariant. Now, since we have to keep this definition vector dot covector, which we just did, it looks like that. How do we do that with this new operator here? Okay, there's only one way you can do it, which is to call this dxj, which will give the Kronecker delta. So it will equal a scalar. Okay, well, this thing here is called a one form, and they're typically denoted with Greek letters like this. So in local coordinates, omega would equal omega I. See, it's covariant, dxi contravariant. Okay, in tensor calculus, we typically thought about vectors as oriented lines, as segments, and covectors as stacks of planes, right? So a vector would pierce X number stacks of planes, and we've done that before. In differential geometry, we need to think of vector fields and covector the fields. Covector fields are actually contour maps, and they're called one forms. Okay, we need to start thinking in terms of fields. All right, if f is a scalar, the function little d of f, we're going to learn later, this is called the exterior derivative. It's a gradient of that function, and it is a one form. Now, we were taught that the gradient acts on a scalar field and produces a vector, as in this. Remember this from calculus? We had the del operator, which is a vector. It acts on a scalar, the field, and it gives a vector. Well, if del f is a tensor rank 1, a vector, then it's got to follow the tensor syntax rules, which we've spent years, right, in studying these things. So it has to follow the rules. So here's the way you would write it in summation notation, except it's not in summation notation. You have a covariant component and a covariant basis vector. Well, this is not a tensor equation. I don't know what to do with this. How would I expand that? I don't know what it means. All right. What about this one? What if we had a covariant component and a contravariant basis vector? Well, that is a tensor equation. I know what to do with this. I know how to expand that. Well, what has a covariant component and a contravariant basis? A covector. Yes, the gradient is a covector. It is a one form. I know it's upsetting. It upset me too the first time I learned about it. So let's compare the tensor transformation of vectors and covectors so I can convince you even more that it's true. Okay, if we have a vector written like this, we want to transform its components to a new coordinate, the system. We always do this the same way. So we call the new one I prime, the old one I. For every index, we need a Jacobian factor, right? This is our free index, so it has to stay in the same place. This becomes a summation index. And what does this mean? It means the partial of the new coordinates with respect to the old coordinates, okay? Now, what about a covector? Well, its components have a covariant index, right? So this is your free index now, which means this is your Jacobian factor. Well, look at that. That is exactly the opposite of that, right? It's the inverse. And what about the gradient that we're trying to define? What about its component? Well, if you look at this, it has exactly the same transform rules as the covector. So it is a covector. This D acting on F, which we're going to talk about this later, is called the exterior derivative. So the gradient is a one form. Okay, so here's our problem. Given some scalar field, x squared plus y squared, which is a circular paraboloid. I love paraboloids, you know that. Express the gradient d of f as this. Okay? Part B, evaluate the gradient at a point, I made it up, 1, 1. Now, given the vector, this vector, so these are its components, these are its basis vectors written in the format of differential geometry. Find the scalar value of df acting on this vector. So we're going to act, what you found acts on this vector at that point 1, 1. And it's going to give a scalar. Okay? D, what is that? What's this scalar number mean? What does it mean? I just found this number. What is it? What's it for? Okay, I'll post the answer tomorrow. I'll see you later.